Hello everyone, welcome back. Today's lesson 221, day 2. Again, we're going to continue our discussion of transformations of other functions, such as absolute value functions, rational functions, cubics, and so on. So we're going to talk more about how to transform those today, move them around, stretch them, reflect them, so forth and so on. We're also going to be reviewing inputs and outputs of functions, so we're going to revisit that topic since it's going to pop up again on the quiz at the end of the week. And we're also going to talk about factoring, which will be on the quiz at the end of this week. So we'll see those two things kind of tie together today. All right, so let's look at our first. All right, so we have a function g of x, and we see that it is x squared minus 6x minus 16. And what they're asking us to find here is g of negative 1. So notice that the negative 1 is inside of the parentheses, so that means that this negative 1 is an input. So that means wherever we see an x in this function, it needs to be replaced with a negative 1. And this one's kind of different because there are two locations where there's an x, so we have to make sure that we replace both. Okay, so we'll have one here and a negative 1 here. So I'll write that out. So we're going to have g of negative 1 equals, and see how we have an x squared. I'm going to replace that x with a negative 1, so instead of x squared, we'll have negative 1 squared. And then we'll have minus 6 times x, but instead of 6x, we'll have 6 times negative 1. So notice that the negative 1 was put into two different locations here. That tends to confuse students, okay? So then we still have a minus 16 that goes on the end. All right, and then we're just going to follow our order of operations here, being very careful with all of these negatives and making sure that we go in the correct order. Okay, so the first thing is parentheses, but the only thing that we have in parentheses are the negative ones, so there's no way to simplify anything in the parentheses. So the next thing we look for are exponents, and we do have an exponent here, so we're going to do negative 1 squared. And negative 1 times negative 1 is a positive 1. So we have 1 minus 6 times negative 1 minus 16. And then we start looking for opportunities for multiplication and division. So there is a multiplication here with this minus 6 and a minus 1. So it's a negative times a negative, which is going to turn into a positive. So this will turn into 1 plus 6 minus 16. And then we'll go ahead and add from left to right. 1 plus 6 is 7. And then 7 minus 16 is negative 9. So if I put a negative 1 in, I'll get a negative 9 out. So in other words, we can write that as g of negative 1 equals negative 9. And that's how I would leave that. Okay, negative 1 in, negative 9 out. All right, let's try this one. Now this one says find x if g of x equals 0. So notice they did not give us the number inside of the parentheses this time. Instead, they gave us the other side of the equal sign. So this is an output. Right? They gave us this number at the end, right? And they want the number at the end to be a 0. So essentially what they are telling us is they want x squared minus 6x minus 16 to equal 0. Right? And we need to figure out what value or values of x will give us that 0. And you might be thinking, well, this looks a little familiar because it's a quadratic set equal to 0. And you would be correct. And you have two options to solve this. You can use quadratic formula, where you figure out what a, b, and c are, and set up your quadratic formula, or you can use factoring. I prefer factoring if it works. So I'm going to set up my box and diamond. There we go. So remember, factoring starts by taking the x squared term and placing it in the upper left-hand box. So I've got x squared here. The constant term on the n, the negative 16, will go in the bottom right-hand box. The negative 6x, that's going to get split up between the two remaining boxes, but we have to do that strategically. So to figure out how to split up that negative 6x, I'm going to take the negative 6x and put it in the bottom of my diamond. The top of my diamond is whatever the result of the multiplication between this first diagonal is. So if I multiply negative 16 times x squared, I get negative 16x squared. So I'm looking for two numbers that multiply to negative 16 and add to give me negative 6. And again, you might have to think about it for a little bit. You might have to try some different combinations. Here's the correct numbers. Negative 8 times 2 is negative 16. Negative 8 plus 2 is negative 6. So these two numbers will work. So I'm going to put negative 8x and a positive 2x in my diagonal. Now I figure out my outside numbers. So I'm going to have x, and then x times something gives me 2x. Well, that's got to be a 2. So x times 2 is 2x. And x times negative 8 will give me the negative 8x. Now we can see our two factors. So we're going to have x minus 8 and x plus 2 equals 0. Right? So this is equivalent to what we started with. And now that we're in this form, this should be really easy to solve. If I take x minus 8 and set it equal to 0, we'll find that x equals positive 8. This is using the zero product property. We can do the same thing here with x plus 2. So we can say x plus 2 equals 0 and solve, and you'll find that x equals negative 2. So this is one solution. This is another solution. So if I were to take an 8 and plug it in for x, I would get a 0. If I were to plug in a negative 2 for both x's, I would also get a 0. So there are two solutions that could make a 0 become the output. All right, guys, that's enough for review for today. Let's take a look at our transformations discussion. So yesterday we kind of went over these four new types of functions. Not really new. We've seen them before. We've seen rational functions and cubics and things like that before, but we've never tried to transform them. And we talked about their names, and then we talked about the graphing form for each kind. Okay, so these are definitely four things you're going to want to know. And you need to make sure that you are reading your clues and looking at your graphs, recognizing the shapes, or recognizing something that might say, hey, we're dealing with an absolute value function, so my equation needs to look like this. Okay, let's take a look at a couple of examples. So going from a description to an equation, right, we are going to take a look at our first clue here. It says that we're dealing with an absolute value function. Okay, so I'm going to take a look up here. My absolute value function looks like this. So if I want to write an equation in graphing form for this thing, I'm going to make sure that I start with its blueprint. And then I'm going to go through and make sure that I find A, H, and K. I need to find those three things. All right. So the A value is a stretch factor. So I'm looking for a clue that might be talking about stretching or compressing. And I notice here in clue 4 it says it has been stretched by a factor of 3. So that means when I write my equation, I can put a 3 in for A. The H value tells me about shifting to the left or to the right. So I'm looking for a clue that talks about shifting left or right. And I see that here in clue 2. Okay, so in clue 2, it's been shifted left 2 units. To shift to the left, I need a plus 2 for my H. The K value tells me about shifting up or down. So here in clue 3, we see it's been shifted down 5 units. So to go down 5, I need a minus 5 on the end. And that completes my equation. Now if I go over here, this one says that we have a cubic function. A cubic function looks like this. It has an exponent of 3, very similar to the quadratics that we were doing last week. So I'm going to start by writing my blueprint. And I'm going to make sure I look for my 3 clues. So again, for the A value, we're looking for a stretch factor or a compression factor. And I see here in clue 4 that it's been compressed by a factor of 0.2. So I'm going to put a 0.2 in for A. Now H and K, those come from left and right and up and down movement, right? So the H represents our left and right movement, and the K represents our up and down movement. Now it doesn't say specifically that it's been moved left or right or up or down, but it does tell us that it has a locator point of 8, -3. Okay. Now if you remember our table from yesterday, remember that the locator point for the original cubic function, right, before it's been moved or stretched or translated or anything, it starts with a locator point at 0, 0. Okay. And in our problem, our locator point is at 8, -3. So to go from 0 to 8, it had to have moved to the right. To move right, we need to do a -8. So moving it, or subtracting 8 inside of the parentheses will move it to the right 8, giving it an x coordinate for the locator point of 8. Now the minus 3 would tell me that it has moved down 3 units. So for the k value, I'm going to say minus 3. The last clue here that I haven't considered yet is clue 2, where it says it's been reflected over the x-axis. To perform a reflection, we need a negative in front of the a value. And that completes our equation for that one. All right, last two examples here. This one says write the equations of the following graphs, and we're allowed to assume all stretch factors are either 1 or negative 1. Okay, so first we take a look at the shape of the graph. I can tell by the shape of this graph that this is a rational function. So I look at this thing, and then I would compare it to my graphs up here. And that looks a lot like this, which is a rational function. So I know my equation is going to have this form. And then I start looking for my clues. Now, they did tell me that my stretch factor can be 1 or negative 1, so that's what I'm going to put here for A. Now, to determine if it's 1 or negative 1, I need to figure out if it has been reflected. So I'm going to go look at the parent graph, which is this one. Okay, so notice before it's been reflected, before anything's been done to it, I have a curve here in the first quadrant and another curve over here in the third quadrant, right? So if it were reflected, this curve would reflect up here, and this one would reflect down here. So these two curves would switch to this quadrant and this quadrant. Okay, so let's go see what quadrants our graph is in. So we are in the first and the third, so this would tell me that it has not been reflected as the curves remained in their original quadrants here. Okay, so that means A is 1. Now, the h value and the k value can be found by looking at the locator point. So remember, the locator point for all of these functions usually starts over here at 0. So this particular point, or this particular locator point, has moved. It has moved left 3 units. And to move left 3 units, we need a plus 3. It has also moved up 2 units. So we need a plus 2 for the k value. And that completes my equation for this graph. So let's take a look at this one. This is a V-shape, and if you're looking at your table up above, you'll remember this is an absolute value function. So we need a absolute value x minus h plus k. And I need to go through and find my clues, right? I need to find my a, h, and k values. Okay, so this V opens downwards. So much like the parabola, if it opens downwards, that means it's been reflected. So I'm going to put a negative 1 in for the a value. Then I use my locator point to determine how it moved. Remember, if it hadn't moved at all, it would be at 0, 0. But this one is not at 0, 0. So I go from 0, 0 to the left 1. Right? So it went left 1, so I need an x plus 1. And then it went up 2. So that means we need a plus 2. That completes my equation for this graph. Alright guys, that's it for today. Give the practice problems a try. Let me know if you have questions.